when you have non-concurrent force systems, you need to do more than just sum forces in the x and the y for equilibrium. Instead, you also have to get some sort of capture of the rotational effect of forces. So, for instance, here we have this worker who is attempting to open up a hopper in the bottom of this rail car, and of course he's got a big long lever bar, and he's going to pull down on it, and that's going to create a torque on the shaft. But first we capture what the moment is of that force. So remember, in 2D we think about a force having two components, the x and the y components. Those are the projections of those two forces onto the orthogonal axes. And when it comes time for calculating the twisting effect of a force, such as we have down here, a force acting along this line of action that passes through point B, it's downwards to the right, we could represent that moment with respect to this point A vectorially as r cross F. And that's convenient if you're doing two-dimensional kinds of work, or rather three-dimensional kinds of work. But in 2D work, it's oftentimes just as easy, and actually quite a bit easier, to work with not the position vector, but rather the perpendicular distance from the point of interest over to the line of action of the force. And we can capture that moment about A then as then that perpendicular distance multiplied by the magnitude of our force. And of course here we would have a clockwise direction. We'd always want to have that direction that would go along with this. Now sometimes it's easier to break apart the force into its components. We could do that. So there's your y component that's acting down, in this case fx, the other one. Now when you do that, then you want the perpendicular distance that is going on from each one of these. So that's in the vertical direction, so we'll call that d sub y. This other one has that direction in the x, so we'll call that way. Now notice what happens here. Fx would tend to want to spin in a counterclockwise way about A, whereas Fy wants to go in the other direction. So when we get this sum total here for our moment about A, then when we sum all this up, we got to account for that. So let's make sure that we've got a symbol here that tells us what we're doing. There's clockwise positive. Our Fy component times dx is going in the clockwise direction, so that's a plus. The other one's going in the other direction, so that would be, in this instance, our dy times fx for our net. Right now, if you go and look at the cross product and how that all works out, you'll see that the cross product approach automatically takes care of a direction. It assumes a very specific direction that is positive for rotational effects, having to do with the right-hand rule for the Cartesian coordinate system. And you don't have to do this ad hoc trying to figure out which is a plus and minus kind of direction. But when you do it scalar, it's a lot easier to work with, and all you have to do is figure out, hey, if I pin this here and I got this component Fy, the force will tend to want to spin that way, or reset it, and we've got the other force, Fx component, going the other direction. That's going to want, of course, tend to want to rotate the opposite direction. Hence, we can keep track on the fly with the plus and the minus.